welcome to this problem walkthrough. Today, we'll tackle problem number 898, titled Bitwise ORs of Subarrays. This problem challenges us to explore bitwise operations and optimize our approach for analyzing subarrays. Let's dive in and unravel the solution step by step. Here, we are tasked with finding the number of distinct values obtained by performing the bitwise OR operation on all possible subarrays of a given integer array, OR. Remember, a subarray is a contiguous segment of the array. For example, if the array is A, B, C, the subarrays include A, B, C, A, B, B, C, and A, B, C. The bitwise OR for a subarray is computed by applying the OR operation sequentially to all its elements. For instance, the OR of X, Y, Z would be X, Y, Z. The challenge is to calculate how many unique values result from this operation across all subarrays. The input array has constraints. Its length can go up to 50,000, and its elements range from 0 to 10 to the power of 9. The output is simply an integer, representing the count of these distinct bitwise OR results. To understand the problem better, let's look at an example where ARR is 0, 1, 2, 3. The goal is to compute the bitwise OR for all possible subarrays. Starting with single-element subarrays, we have 0, 1, 2, and 3, which result in OR values of 0, 1, 2, and 3, respectively. Moving to subarrays with two elements, 0, 1, results in 0, 1 equals 1, 1, 2, gives 1, 2 equals 3, and 2, 3, also gives 2, 3 equals 3. For three-element subarrays, 0, 1, 2, results in 0, 1, 2 equals 3. Notice that as subarrays grow larger, the bitwise OR tends to accumulate higher values or stay the same. Continuing with the example, for the four-element subarray, 0, 1, 2, 3, the result of the bitwise OR is 0, 1, 2, 3 equals 3. After analyzing all possible subarrays, the distinct OR values are 0, 1, 2, 3. Therefore, the total count of unique values is 4. Now, consider another example where ARR is 1, 2, 4. Starting with single-element subarrays, 1, 2, and 4 yield OR values of 1, 2, and 4. For two-element subarrays, 1, 2 gives 1, 2 equals 3, and 2, 4 results in 2, 4 equals 6. For the three-element subarray, 1, 2, 4, the result is 1, 2, 4 equals 7. In this second example with ARR equals 1, 2, 4, the distinct OR values are 1, 2, 3, 4, 6, 7, so the total count is 6. Another scenario to consider is when all elements are 0, such as ARR equals 0, 0, 0. Here, no matter the size of the subarray, the bitwise OR will always be 0. For example, 0, 0, 0, or 0, 0, 0 all result in 0. Therefore, the only distinct value is 0, and the output is 1. These examples illustrate how the problem is solved by evaluating every subarray and identifying the unique OR values they produce. When solving this problem, it's important to consider edge cases. For instance, if the array contains only one element, the output will always be 1 since there's only one subarray. Similarly, if all elements in the array are 0, the result will also be 1 because the bitwise OR of any subarray will be 0. For large arrays, the algorithm must be efficient enough to handle up to 50,000 elements without exceeding time limits. Finally, test cases with very large values, up to 10 to the power of 9, should also be considered to ensure the solution works correctly within the constraints. To start, let's consider the brute force approach. The intuition here is straightforward. We iterate through all possible subarrays of the given array, calculate the bitwise OR for each subarray, and store the results in a set to ensure that only unique values are kept. A subarray can be represented as RR, ij plus 1, and for every subarray, we compute the OR of all elements in that range. Once all subarrays have been processed, the size of the set will give us the total number of unique results. For implementation, we use two nested loops. The outer loop selects the starting point of the subarray, and the inner loop extends the subarray while updating the current OR value. However, this approach has significant limitations. The time complexity is quadratic, n squared asterisk k, where n is the length of the array and k is the maximum number of bits in the integers, making it computationally expensive for large arrays. Additionally, the space complexity is n for the set. Therefore, while this method is simple and intuitive, it becomes impractical for larger input sizes due to its inefficiency. Now, let's explore the optimized approach, which uses a sliding window with sets. The key observation here is that the bitwise OR operation is inclusive and accumulative. This means that once a bit is set to 1 in the result, it cannot revert to 0. Using this property, we can avoid redundant computations by maintaining a sliding window of OR results. Here's how it works: we keep track of all OR results ending at the current element in a set called current. We also maintain a set called previous to store the OR results from the previous iteration. For each new element in the array, we compute the OR of that element with each value in previous and add the results to current. Additionally, the OR of the element by itself is also added to current. Finally, all values in current are added to a global result set, ensuring that we only store unique results. This approach leverages the accumulative property of OR, significantly reducing redundant calculations. By the end, the size of the result set gives us the desired count of unique OR results. In terms of complexity, this optimized approach has a time complexity of O(n*k). Here, k represents the number of bits in the integers, and the operations are efficient because the size of previous is limited by the number of unique OR results, which depends on k. The space complexity is O(n) for the sets used to store intermediate and final results. This method offers several advantages over the brute force approach. It's significantly more efficient for large arrays, as it avoids redundant computations by leveraging the accumulative property of bitwise OR. When comparing the two approaches, brute force is simpler to implement but computationally infeasible for large inputs due to its high time complexity. On the other hand, the sliding window with sets is both efficient and straightforward, striking a balance between performance and code clarity. For these reasons, the sliding window approach is the preferred strategy. It provides a substantial performance improvement for larger input sizes while remaining easy to implement, making it the optimal choice for solving this problem. In this problem, we need to determine the number of distinct values obtained by applying the bitwise OR operation on all possible subarrays of a given array. To break this down, a subarray is any contiguous portion of the array, such as R, ij plus 1, or I and j are valid indices. The bitwise OR operation is performed on two numbers by comparing their binary representations and setting each bit to 1 if at least one of the two bits is 1. For example, if we compute 5 or 3, the result is 7 because the binary representation of 5 is 101, 3 is 011, and their OR operation yields 111, which is 7 in decimal. The brute force approach involves generating all subarrays, calculating the OR for each, and storing unique results in a set. However, this approach is inefficient, with a time complexity of O(n superscript 3, because generating subarrays takes O(n superscript 2, and calculating the OR can take O(n) for each subarray. To optimize, we aim to avoid redundant calculations by leveraging overlaps in subarrays and reusing previously computed results. To achieve this optimization, the algorithm uses two sets. The first set, current, keeps track of the OR results for subarrays that end at the current index. The second set, unique, stores all distinct OR results across the entire array. As we iterate through the array, we update the current set by computing the OR between each value in current and the current element of the array, R, I. We also add the current element itself to account for subarrays that start and end at the current index. After updating current, all its values are added to the unique set to ensure we capture every distinct result. Finally, the size of the unique set gives us the total number of distinct OR results. The key insight here is that subarrays ending at index I significantly overlap with those ending at index I1, allowing us to reuse results efficiently. Additionally, the nature of the OR operation means that it tends to accumulate bits, limiting the growth of unique results and reducing the algorithm's complexity. Two key data structures are involved in the algorithm. The current set efficiently tracks OR results for subarrays ending at the current index, and its size is limited by the number of unique OR results, which is relatively small. The unique set ensures that all results are distinct, and operations like insertion and membership checks in a set are efficient, averaging O(1) time. In terms of complexity, the algorithm iterates over the array in an outer loop, which takes O(n). Within the loop, the current set processes a limited number of elements because the number of unique OR results is bounded by the number of bits in the integers, typically 32 for 32-bit numbers. This makes the inner processing effectively O(1) per iteration. Overall, the time complexity is O(n), and the space complexity is O(u), where U is the number of unique or results. For example, with the input array 1, 2, 3, we initialize current and unique as empty sets. As we process each element, we progressively update these sets to capture all distinct OR results while efficiently reusing previous computations. With the input array 1, 2, 3 in the first iteration, we process the element 1. The subarray 1 produces an OR result of 1, so current becomes 1. We add this to unique, making it 1. In the second iteration, we process the element 2. We compute the OR of 2 with all elements in current, which is just 1 or 2 equals 3. We also add 2 itself as a new subarray. This updates current to 2, 3. Adding these values to unique results in 1, 2, 3. In the third iteration, we process the element 3. Computing the OR of 3 with all elements in current gives 2 or 3 equals 3 and 3 or 3 equals 3, so no new values are added. Adding 3 as a standalone subarray results in current equals 3. Adding this to unique leaves it unchanged as 1, 2, 3. The size of unique, which is 3, represents the total number of distinct OR results. This example demonstrates how overlapping subarrays and the cumulative nature of the OR operation streamline the process while ensuring all distinct results are captured. Certain edge cases highlight the robustness of this algorithm. For a single element array, such as ARR equals 5, there is only one subarray, so the result is 1. When all elements are equal, such as ARR equals 4, 4, 4, the OR operation repeatedly produces the same result, so the total is also 1. In the case of all zeros, such as ARR equals 0, 0, 0, the OR operation on zeros always results in 0, leaving the total distinct count at 1. The Python implementation of this algorithm is straightforward. We define a function subarray_bitwise_ORs that initializes unique and current as empty sets. For each element in the array, we update current by computing the OR between the current element and all existing values in current, as well as adding the current element itself. Then, we update unique with all values in current. Finally, we return the length of unique, which gives the total number of distinct OR results. For example, inputting 1, 2, 3 into this function outputs 3, as we calculated earlier. This optimized approach ensures the algorithm is both efficient and easy to understand. By leveraging the properties of the bitwise OR operation, the algorithm avoids redundant computations, uses minimal additional space, and scales well with input size. The use of sets simplifies the process of tracking unique results and guarantees efficient operations. Overall, the combination of clear logic, effective reuse of intermediate results, and robust handling of edge cases makes this solution a practical and elegant way to solve the problem. This implementation solves LeetCode problem number 898, Bitwise ORs of Subarrays, by efficiently computing the distinct results of bitwise OR operations for all possible subarrays of an input array. The function subarray bitwise ORs takes an integer array ARR as input and returns the count of distinct values obtained from bitwise OR operations on all contiguous subarrays. The solution uses two sets. Result: this stores all unique results of bitwise ORs across subarrays. It is updated iteratively. Current: this tracks the bitwise OR results for subarrays ending at the current element in ARR. Each iteration updates this set with the current number and the OR results of the previous subarrays combined with the current number. The loop iterates over each number in the array. For each number 1, it computes the new current set by taking the union of the current number and the OR of the current number with each value in the previous current set. 2, the results from current are added to result to maintain all unique bitwise OR values. 3, this approach ensures that we only store the necessary results without redundantly recomputing for overlapping subarrays. Finally, the function returns the size of the result set, representing the total number of distinct bitwise OR results. This algorithm is highly efficient, achieving near linear performance in practice due to the limited size of the intermediate sets, which are constrained by the number of unique bit patterns in the input numbers. This makes it well suited for the problem's constraints. This is the Java implementation of the LeetCode problem number 898, Bitwise ORs of Subarrays, following the same logic as the provided Python code. The solution uses two sets, one to store all unique results of Bitwise ORs and another to maintain intermediate results for subarrays ending at the current position. Key differences include explicit type declarations, the use of Java-specific collections like hashset, and a slightly different syntax for set operations. The final result is the size of the set containing all unique bitwise or values. To solve this problem, we want to compute all unique results of bitwise or operations for the subarrays of the input array 1, 2, 4. We start by initializing two sets, result, which will store all unique or values across the entire array, and current, which will track OR results for subarrays ending at the current index. First, we process the element 1. Since current is initially empty, the OR operation produces just 1. We update result with this value, so result is now 1. Next, we process the element 2. The new current set is computed by performing bitwise or between 2 and every value in the previous current, along with the element itself. This gives 2, 3, as 1, 2 equals 3. We add these values to result, updating it to 1, 2, 3. Finally, we process the element 4. The updated current set includes the results 4, 6, 7, based on OR operations with the previous current, as 2, 4 equals 6 and 3, 4 equals 7. Adding these to result, we now have 1, 2, 3, 4, 6, 7. At this point, the final output for the input 1, 2, 4 is determined by the size of the result set, which is 6. Now, let's consider another example with input 1, 1, 2. We start by initializing result and current as empty sets. Processing the first element 1, the OR operation produces 1. We update result with this value, so result becomes 1. Next, we process the second element, which is again 1. The OR operation here results in 1 as well, since combining 1 with the previous current set does not produce any new values. Therefore, result remains unchanged at 1. Finally, processing the element 2, we compute a new current set as 2, 3, because 1 to 2 equals 3. Adding these to result, we get 1, 2, 3. The size of result is 3, so the output for this example is 3. In our third example, with the input 3, 7, 15, we again initialize result and current as empty sets. Starting with the first element 3, the OR operation gives 3, and we update result to 3. Next, we process the element 7. The OR operation between 7 and the previous current set, 3, results in 7, since 3, 7 equals 7. Updating result now gives 3, 7. Finally, we process the element 15. The new current set becomes 15, as 7, 15 equals 15. Adding this to result, we obtain 3, 7, 15. The size of result is 3, so the output for this example is also 3. From these examples, we can observe key details about the algorithm. The current set captures all possible OR results for subarrays ending at the current index. It is updated by combining the current element with all previous results stored in current, ensuring we systematically account for every subarray. Meanwhile, the result set accumulates all unique OR values across the entire array. Using sets allows us to avoid duplicate values and ensures efficient computation. Regarding complexity, the time complexity is O(n*32), which simplifies to O(n), since each integer has at most 32 bits. The space complexity is also O(n), to maintain the current and result sets. This approach is both efficient and effective for solving the problem. To analyze the time complexity of this solution, we start by observing that the algorithm iterates through the array ARR once, meaning the outer loop executes n times, where n is the length of the array. For each iteration, a new set called current is created. This set contains the current number and all distinct results of bitwise OR operations between the current number and each element in the previous current set. A key insight here is that the size of the current set, which represents all distinct OR results for subarrays ending at the current index, is bounded by W. This W is determined by the maximum number of bits required to represent the largest number in ARR. For example, if the largest number in ARR is less than 2k, then W equals k. Additionally, the work done per iteration involves performing bitwise OR operations for each element in the current set. Since the size of current is at most W, this step takes O, W, time in the worst case for each iteration. The total time complexity arises from the combination of the outer loop and the work done per iteration. The outer loop runs n times, and within each iteration, the algorithm processes at most W elements. This gives a total time complexity of O, n*W. Since W is proportional to the number of bits needed to represent the largest value in ARR, we can express W as O log max R. As a result, the final time complexity of the solution is O n*log max R. This shows that the algorithm efficiently scales with both the size of the array and the magnitude of its largest element, greatly improving over a naive approach. Now, let's consider the space complexity of the solution. The result set, which stores all distinct bitwise OR results across all subarrays, is a key contributor to memory usage. The size of this set is determined by the total number of distinct bitwise OR results, which is bounded by O n*log max R in the worst case. Additionally, the current set, which temporarily holds the distinct OR results for subarrays ending at the current index, is bounded by O log max R. Aside from these sets, the algorithm uses constant space for variables and temporary storage, which is O(1). Combining these factors, the overall space complexity is dominated by the result set, leading to a total space complexity of O n*log max R. When comparing the optimized approach to a brute force solution, the differences are significant. A naive method would involve generating all possible subarrays of ARR, computing the bitwise OR for each, and storing the results. Since there are O(n²) subarrays and computing the OR for each subarray takes up to O(k) time, where k is the subarray length, this approach results in a worst-case time complexity of O(n³). Additionally, the space complexity of the brute force method is O(n²), due to storing all subarray results. In contrast, the optimized solution avoids redundant computations by leveraging the current set to reuse results from overlapping subarrays. This reduces the time complexity to O n*log max R and the space complexity to O n*log max R. These improvements make the optimized approach far more efficient, especially for large inputs, as it minimizes both redundant operations and memory usage while exploiting the properties of bitwise OR. One common mistake when solving this problem is failing to use a set to store distinct results. Without a set, duplicate values are included in the output, leading to an inflated result size and unnecessary computation. Sets handle duplicates automatically, so this issue can be resolved by leveraging them effectively. Another issue is relying on a brute force implementation that explicitly generates all subarrays. This approach involves nested loops and often includes slicing arrays repeatedly, which increases the time complexity to O(n³). Instead, you can optimize by computing results directly while iterating, avoiding the need to explicitly create subarrays. Finally, neglecting edge cases can also cause incorrect outputs. Scenarios like empty arrays, arrays with only one element, or arrays where all elements are identical often reveal hidden bugs. Testing these edge cases ensures your solution is robust and handles all input variations correctly. Another challenge arises from misunderstanding how the bitwise OR operation behaves. Some might incorrectly assume that OR resets bits, leading to flawed implementations. In reality, the OR operation combines bits, meaning that a bit is set to 1 if it's 1 in either operand. To build intuition, it's helpful to dry run small examples and observe how the OR propagates across bits. Additionally, overlooking space complexity can lead to inefficient solutions. For instance, creating intermediate arrays for each subarray consumes a lot of memory unnecessarily. Instead, you can minimize auxiliary space by using in-place computations and sets to track results, which keeps the solution efficient. In interviews, it's helpful to recognize key patterns and problems involving distinct bitwise OR values. A reliable approach is to use a set to track results while avoiding redundant computations. Optimization often involves maintaining rolling results for overlapping subarrays instead of solving for all subarrays explicitly. Discussing trade-offs is also important. While brute force methods are simpler to explain, optimized solutions are faster but more complex. Demonstrating your understanding of both approaches showcases your problem-solving ability. Edge case analysis is another critical step. Clarify scenarios like arrays with all zeros, all ones, or extreme lengths. For example, very small arrays may allow simpler solutions, while very large arrays may necessitate optimization. Lastly, ask clarifying questions about input constraints, such as the maximum array size or value ranges. This helps determine whether solutions with higher time complexity are acceptable in the given context. Several related problems share concepts with this one. For example, LeetCode 421 focuses on finding the maximum XOR of two numbers in an array, while LeetCode 1442 deals with counting triplets that can form two arrays with equal XOR. LeetCode 1521 explores finding a value closest to a target using a mysterious function, and these problems all involve bitwise operations or set-based tracking techniques. When it comes to alternative approaches, dynamic programming offers an optimized solution. By maintaining a rolling set of OR results for the current subarray end and propagating them to the next element, you can reduce redundant computations. This approach achieves O(n)² time complexity, making it more efficient than brute force, though slightly more complex to implement. Another option is sliding window with bit masking, which dynamically computes OR values and avoids redundant recalculations. While this method is highly efficient, it can be more challenging to debug and is best suited for very large inputs. Finally, divide and conquer provides another alternative approach. This strategy involves dividing the array into halves, solving for each half independently, and then merging the results. While this approach doesn't always improve performance, it can simplify recursive implementations, particularly for certain problem variations. Divide and conquer is a flexible strategy that's worth considering when you're working with variations of this problem, as it can help break down the problem into manageable pieces while still ensuring that all subarray results are accounted for in the final output. Great work! To wrap up, we reviewed an efficient solution to the problem, focusing on bitwise operations and optimization techniques. Remember, practicing problems like these sharpens your coding and problem-solving skills. Thank you for watching, and don't forget to like, share, and subscribe for more content like this. See you in the next video. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!